Hello everyone. Today we're going to take a look at a summary of available tests for convergence or divergence of infinite series. So first little note here, there's actually one sequence test for convergence. So let me just make a note of that. So the sequence test for convergence of a sequence, so that was from section 11.1. That one says this: if the limit is n approaches infinity of a sub n, so the nth term of the sequence, if that equals L, where L is a real number, the sequence converges. Okay, so that's for a convergence test for a sequence or just one of them. I'm never going to ask you about that, but it came up because when we were talking about series, we were talking about a sequence of partial sums of the series. So it came up sometimes, but basically there's just the one sequence test for convergence, which essentially says that the limit exists, the sequence converges, as in 11.1. Again, I'm not going to ask you about that one, but I just wanted to put it here. It seems like it belongs in this page with all the series tests. So now let's take a look at the series test. So the first one that we saw was the test for divergence, which goes also by the divergence test and the nth term test. This one was in section 11.2. And basically it says this: if the limit is n approaches infinity of a sub n, the nth term is not equal to 0, or the limit is n approaches infinity of a sub n does not exist, then the series diverges. Okay, and the test for divergence is nice because it's really fast and really easy to use, but the drawback is normally when you take the limit you get 0, and that note takes care of that situation, because if we take the limit as n approaches infinity of a sub n and we get 0, basically we know nothing about the convergence or divergence. So the test is inconclusive. So when that happens, that just means we need to use a different test, right? Okay, so test for divergence was in 11.2. Another one that was in 11.2 was a geometric series test. And conditions for use: there must be a constant ratio r between any two consecutive terms. So if you look at one term and multiply by r, you get to the next term. Multiply that by r, you get to the next term, and so forth. So once you find r, if the absolute value of r is less than 1, which means that r is between -1 and 1, then the series converges and it has a sum of a over 1 minus r. Remember, a is the first term of the series, okay? But if the absolute value of r is greater than or equal to 1, which means that r is greater than or equal to 1, or r is less than or equal to -1, in that case the series diverges. Okay, so those first two were from section 11.2. Then we had section 11.3 and the integral test. This is the test that's it's a bit of a handful sometimes, so you want to only use this if you have to, if there's nothing else that will work. So conditions for use: the function f of x, which is the corresponding function to our series, f of n equals a sub n, must be continuous, positive, and decreasing. So typically to show continuous and positive, you can just sort of tell by, eyeballing them, and maybe, on your test, make a note. You check it's continuous, it's positive. Decreasing, we typically have to show, right? So the normal way is you take the derivative of the function and find out where the derivative is negative, because where the derivative is negative, the function is decreasing. Or you could take the actual series, and if you get lucky, if the numerator is a constant term, you could maybe show that b sub n plus 1 is less than or equal to b sub n or something like that. But one way or the other, we have to show that the function is decreasing. So the conclusion here is this series is convergent if this improper integral involving the corresponding function is convergent, which means, in other words, if you evaluate this improper integral, which requires limits, right? Requires limits, and if you get a number, a real number, then this converges, and if this converges, then the series converges. On the other hand, if you integrate this improper integral and you get like a infinity or negative infinity, or just find that it doesn't exist, then the series is divergent. Okay, so that was from 11.3. Also from 11.3, we had the p-series test. Conditions for use, we have to have a p-series, right? So we have to have a series of the form summation from 1 to infinity of 1 over n to the p. And the conclusion is the series converges if p is greater than 1, and it diverges if p is less than or equal to 1. Okay, so that got us through 11.3. Got the first 4 tests out of the way. And then we have the direct comparison test. So section 11.4, we had 2 comparison tests for the direct comparison and the limit comparison. So for the direct comparison, conditions for use, both series and using the comparison must have positive terms. The conclusion is, if this b sub n series is convergent and a sub n is less than or equal to b sub n for all n, then a sub n also converges. So think of it like this. So this series converges, right? B sub n converges, so it adds up to a finite number. And a sub n is less than or equal to b sub n for all n. So a sub n is smaller than b sub n. We know if we add up b sub n, we add up all the b sub n terms, we get a number because it converges. Well, if a sub n is smaller than that, it's going to have to converge also, right? There's no way if this is smaller, it can somehow add up to infinity and diverge, right? Okay, and then the other part of this is that if this series b sub n is divergent and a sub n is greater than or equal to b sub n for all n, well then a sub n also diverges, right? So if b sub n is divergent, so we add this up, it goes to infinity, and a sub n is even bigger. So a sub n is also going to have to go to infinity, right? So b sub n is divergent and a sub n is greater than or equal to b sub n for all n, then a sub n also diverges. Okay, so that was the direct comparison test. Then the limit comparison test, the note here is that we have to select a suitable b sub n. So select a suitable b sub n. A suitable b sub n series. So basically we're going to select a series that we know about. We know this series either converges or diverges. And it'll be a series that we think our series acts like, but we just don't know for sure. Okay, conditions for use. Both series used in the test must have positive terms. Conclusion is the series will both converge or both diverge if the limit is n approaches infinity of a sub n over b sub n equals c, some number greater than 0. And c has to be a number. It's got to be a number. So it can't be infinity, not infinity. That won't work. Okay, so if this were to happen, then both series will converge or diverge. So we already know about the b series, right? We know this series we selected, we know what it does, converges or diverges. So then our series we're testing is a sub n, this series. Okay, so we take the limit, and if we get some number, That b sub n. Let me see if I can clean that up a little bit. Okay. So we take the limit and we get some number, then they both converge or both diverge. Okay, and that's the one that we'll normally do. But there's another two parts to this. So if b sub n converges and the limit as n approaches infinity of a sub n over b sub n equals 0, then a sub n also converges. This one makes sense if you think about it, because this series converges, so it's down here, but this fraction is so dominated by the denominator that the limit is 0. Right, so a sub n is going to have to be smaller, right, than b sub n, because b sub n converges, but it dominates, the denominator dominates the numerator so much that the fraction goes to 0, then a sub n has to converge also. Okay, and then the other part of that would be if this b sub n series diverges and the limit as n approaches infinity of a sub n over b sub n equals infinity, well then a sub n is also going to have to diverge, because b sub n diverges, so it's going to infinity, but a sub n, the numerator so much dominates the denominator that the fraction goes to infinity. So a sub n is definitely going to diverge also, right? B sub n diverges, but you put a sub n over b sub n, and a sub n dominates. The numerator dominates so that the limit here is infinity. So a sub n is also going to infinity, so it's going to also diverge. Okay, then we have the alternating series test. This is in section 11.5. And the note here is b sub n is equal to the absolute value of a sub n. Okay, so conditions for use. The series must be alternating. So we have to have an alternating series to use the alternating series test, right? So the terms have to go back and forth between positive and negative. The conclusion is this: if b sub n plus 1 is less than or equal to b sub n for all n, which basically means the terms are decreasing. So the terms are decreasing. And also the limit as n approaches infinity of b sub n equals 0, then the series is convergent. So alternating series test is a pretty easy one to use. You just show that the terms are decreasing. You show that the limit of the nth term b sub n is 0, and the series is convergent. Now it turns out if this doesn't work, then the series diverges by the test for divergence, right? If you don't get a 0 here, that just means it diverges. Okay, then the absolute convergence test. This is not one that I spend a lot of time on. It is covered in the book, though. So conditions for use: the given series must be absolutely convergent. That is, the series a sub n wrapped up in absolute values must converge. Conclusion is the series a sub n will also converge. Now this makes sense. If you think about, if you take a series and wrap it up in absolute values so all the terms are positive and it converges, then the original series, if you get rid of the absolute value, so maybe there were some positive and negatives in there, well, it's also going to converge, right? Because if you add up all the positives and you don't get infinity, you get some number, then sprinkling some negatives in there, it's just going to make it a little bit smaller, so it would still converge. Okay, so that is the absolute convergence test. And then that brings us to the last section, 11.6, which has the last two tests, the ratio test and the root test. The note here for the ratio test is factorials. So when you see factorials in a series, you want to think right away of the ratio test. Okay, and the conclusions for the ratio test and the root test are very similar, and they look like this. If the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. If that is less than 1, then the series is absolutely convergent. Okay. If, on the other hand, the limit is n approaches infinity of a sub n plus 1 over a sub n is greater than 1 or infinity, if it's infinity, then the series is divergent. And the worst case scenario, if the limit is n approaches infinity of a sub n plus 1 over a sub n, of course in absolute values, these are all in absolute values. If it equals 1, then the ratio test is inconclusive. It means we don't know what it does. Maybe it converges, maybe it diverges. We need a different test. That doesn't happen very often, but it could. Okay, so that is the ratio test. And then the last one is the root test, and it really doesn't come up very often. It's if you have something raised to maybe an nth power, but you don't see it too much. But it's very similar to the ratio test. It basically says if the limit is n approaches infinity of the nth root of the absolute value of a sub n, if that is less than 1, then the series is absolutely convergent. Okay, and also if the limit is n approaches infinity of the nth root of the absolute value of a sub n is greater than 1, then the series is divergent. And I think you can make a prediction about this last line, but just in case you can't, if the limit is n approaches infinity of the nth root of the absolute value of a sub n equals pi? No, of course not. If it equals 1, then the root test is inconclusive. Okay, and that gives you all of the series tests. So if you had this little handout with you when you're working on homework, taking a test or whatever, it'll be very helpful. So you just want to have this printed out and have it next to you when you're working on these convergence questions about series, and should be quite helpful.